welcome to the tinyML world with the global coverage. I think we are broadcasting live to the whole world now. And we are very excited today to start our new project or our new product. It's called tinyML Builds. So this is the place where you're going to meet people, tinyML builders, people who build real tinyML devices in a real world, products, technologies, and the product enabled by tinyML. So we are very, very thrilled and excited to start this new series. And that's simply because tinyML as a technology and as a movement got to the point where the technology foundation is very, very strong. We have many companies like for example, Lattice and others offering great hardware, great silicon for tinyML. We have many tinyML algorithm companies, many tinyML ops companies, software companies, AutoML companies. So basically the whole community, the whole ecosystem has come together. And what happens next, people use tinyML and apply these technologies, software, hardware, everything to solve problems, customer problems, to build new devices, new products, new applications. And that's exactly what this new series tinyML Builds is going to reveal. So again, super thrilled about this. We're going to have it monthly. It's going to be live, and it's going to be super interactive. So we encourage you to ask your questions as we go, and you can think about this like tinyML under the hood. So our guests will be describing what technologies they're bringing to the table, what products these technologies enable to build, how it works, what kind of applications. And again, you're very, very encouraged to ask any type of questions on how they built it, why they did it, what kind of problems they had on the way, how they solve these problems, and what it means, what kind of value it brings to the customer. So any kind of questions. And that's why, again, we are doing this series and bringing very special guests to this series. Just like today, we are very fortunate to have two distinguished guests from Lattice Semiconductors. It's Sreepada V Hegade and Hussein Osman. I remember when we started tinyML back in about 5 years ago, I think Lattice was one of the first companies who participated in this with their FPGA platforms. And in fact, when we started doing tinyML meetups, in-person meetups in the Bay Area before the pandemic, the first one I think we did in Qualcomm, the second one we did at Google, and the third one, Lattice, Hussein hosted it. I think again, Lattice Semiconductor, they've been around in this space for quite some time, and we are very fortunate to have them here today to share their knowledge, their wisdom, their scars, their experience, what they learn in their journey. So before we start, in the usual format, let me acknowledge our strategic partners and sponsors, those are the companies who made this series possible. Again, the new series, it's AZIP, AI, Analog Devices, Adrena, ARM, Compass, Marketing, Edge Impulse, Greenwave Technologies, Gravity Inc., IBM, ImagineMob, Inotera, Microsoft, Nota AI, NXP, OctoML, Pollen Technology, Kixo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST Microelectronics, Synaptics, Syntian, and TDK. So you see a very diverse list of companies in the tinyML ecosystem and more partners there. So that's why, again, we want to bring all this energy and all this knowledge together and share with us. You know that we are strong as a community, so you are encouraged to join this community, the meetup community. There are many groups with tens of thousands of people there. I think our LinkedIn community is very strong and active. All the content and information we have in the tinyML becomes publicly available same week. For this, we have a YouTube channel which is very active. Also, with about 9,000 subscribers and over 500 videos there. This particular event, this particular discussion will be also recorded, and you'll be able to see it this week online on YouTube as well. As I said, in 2 weeks, we will be celebrating the 5th anniversary of tinyML. Our first summit was in 2019. So this is going to be our 5th event. So we are super excited about it. So if you are in the area or if you plan to attend this event, you still can register and attend. I think one announcement for people in the Bay Area, and for people who happen to be in the Bay Area, on Monday the 26th, we are going to have tinyML open house. Basically, the exhibition and all the companies will be available with registration fee waived, basically free. So if you're interested in seeing the latest and greatest and talking to companies, just stop by on the 26th, or I'm sorry, on the 27th on Monday, and also attend the whole summit. I think the program is beyond awesome there. A lot of networking opportunities, and all the key companies are going to be there. And the focus of this year will be on end users and applications. So you're going to see many examples like how tinyML can be used in the real world. Basically, what we are going to cover at this series. And then for the academic community, on Monday the 27th, there will be a tinyML research symposium, the 3rd one, which will be focused on the advancement in the research area in tinyML. Again, very rich program, so super excited about it, and you're encouraged to join. There's one more event is coming, which is also very interesting. It's tinyML EMEA, Europe, Middle East, and Africa event in the end of June. It will take place in Amsterdam, and TPC is working on the program. So we received a huge number of abstracts for this. I think that was the deadline was end of February, and the technical program committee is putting a program together that we plan to have available by the end of the month, and registration will open soon. So it's going to be a very interesting event in Europe, Middle East, and Africa. Next week, we are doing our first tinyML pavilion at the Embedded World in Germany. So 10 companies will be presenting their products in the pavilion, and in parallel, there will be a technical session on tinyML at the Embedded World technical conference as well. Again, this is for those who are going to be at the Embedded World. Just stop by, talk to the companies, or see the technical program. And it is my pleasure and a privilege to introduce our host. It's Dr. Venkat Rangan. So when we started thinking about this series and kind of bounced some ideas back and forth, we were thinking who would be a good host for this. And I think Venkat, I cannot think about a better person for this role as Venkat Rangan for several good reasons. I think Venkat is one of the pioneers of tinyML. In fact, he started his tinyML journey back in around 2015 while he was still at Qualcomm. And since then, he is super passionate about tinyML, and you're going to get this passion from him as we go today. So that's reason number one. Second, Venkat is a very deeply technical person, and he's super technically curious person. He dives into details in many different areas: hardware, software, applications, products, codes, everything, algorithms, models. So, and he has a very deep knowledge in this. So if you have any questions, again, as we go during the presentation, we can go as deep as you want in many of these questions. Then deep in his heart, Venkat is innovator. So he has a lot of patents in this space. And again, his mindset is really how do you use technology to do things, to build things. So that's why, again, he's a great host for this series. Next, he's really a system level type of person. He looks at the problems holistically from the system perspective. His kind of core background is in the hardware, but he's very deep, equally deep in other areas as well, system, algorithm, software, and so on. Then Venkat is an entrepreneur. When he left Qualcomm, it was in about 4 or 5 years ago, he started his own company, tinyvision.ai, and he's been on this journey for many years and accomplished quite a bit working with partners and companies, and that's a great experience to bring to this series. Venkat is a community builder. He has his own channels and he interacts with people. He's very active with high school kids and doing quite a bit in the science, technology, and education area. He has interns in his company doing cool work in tinyML. So a really kind of great person from the community perspective. He's very product oriented, which is also important for this series. And last but not least, and it's very important, he's a really, really nice personality and a humble person. And it's really, I feel really privileged to have Venkat, or call Venkat as my personal friend for many years. And he's a great person to hang around. In fact, I was in San Diego a couple of days. We had dinner with Venkat and a great conversation there. So anyways, I think Venkat is going to be a great host for this series. And Venkat, thank you for taking this role, and the floor is yours at this point.
Thank you so much, Evgeny, for all that. That was very nice to hear. So just a little bit about going back to what Evgeny said. When we started talking about this tinyML builds, it was really with the realization that so far we've been a lot about tinyML has been pushing technology. At some point, I think we've been seeing that there are people who want to actually use this stuff now, and so I like to build things, right? That's what I like to do, and I know a lot of our audience also wants to build stuff. So rather than having a presentation which is more conventional from the companies that have the technology or the product companies, we thought it would be great to have a conversation, a lot like what would happen if you were to go and stop by somebody's booth at a conference, say at CES or Embedded World that's coming up, is go in and have a conversation and try to understand from the point of view of somebody trying to build these devices. What does it take to build a real world device? And that's why we call it builds. So without more talk, I'd like to introduce Lattice Semiconductor today. Sreepada Hegade is the Director of ML Software and Solutions at Lattice Semiconductor. It is enabling machine learning at the edge using Lattice low-power FPGAs. His team is responsible to deliver the SenseAI solution stack, an award-winning neural network inference solution from Lattice Semiconductor. He works closely with the marketing team to deliver solutions that are well-tuned for many vertical market segments like industrial automation, client compute, and so on. He has 20 plus years of experience in delivering software and hardware required to implement leading-edge applications on FPGAs. And our other guest today, Hussein, I've known Hussein for many years as well. We work together, and Hussein is a semiconductor industry veteran, over 2 decades of experience bringing to market silicon and software products. And over the past 5 years, he's been leading the SenseAI solution strategy and go-to-market at Lattice Semiconductor, creating high-performance AI and ML applications. So thank you for taking the time to be here, Hussein and Sreepada. It's great to have you guys here, and maybe we can dig into some details of how things work.
Thanks.
So just a little question that I want to start you guys off with so that we set the stage for the conversation is, as part of tinyML, what is tinyML for you guys? Is it like watts, milliwatts, hundreds of watts, something in the middle?
Let me start there. So tinyML for me is, I think, somewhere below 100 milliwatt in terms of power. It needs to do something significant, some good processing capabilities in that envelope. It also has to be cost efficient as well as power efficient. So, cannot be in more than a few dollars, and it can be always on, or it can be on for periods of time, and you can rest and go to sleep and come and do some significant processing for an amount of time. And so that's how I think of tinyML. And when we started to work as part of the tinyML community, we were working with devices like the ICE40 Ultra Plus, which I know, Venkat, you're aware of. And that device is super low power. It's a size of 5 mm squared. It's a really tiny device, and it can do some significant processing in this area. So when I think of tinyML, I think of that type of a device.
Yeah. Let me add to that, right? So, Venkat, thanks for the nice introduction and hosting us. So, basically, yes, power and all this form factor, and these are very important. But when you look at the overall cost of the solution and bringing it to market on time and winning kind of thing, so what is important in the tinyML is like creating an application easily, like the way we do it today with cloud or any other infrastructure, right? If we can enable the same thing on a smaller device, right? So whole design methodology, creation, and make it very cost effective and a very reliable solution, right? So those are very important in the tinyML. That's what basically one of the things at Lattice we focus on, how to make it very easy for our customer to adopt, right? And develop application and deliver on time for the market, right? So that's basically one of the key aspects of the tinyML for me.
That's great to hear. The ease of use is something that I think is really important in these applications, because just having a bunch of examples is a good start, but also being able to support customers is a huge thing. And, the reliability is also something that's important, I think, in ML. It's on top of all of the IoT stuff that comes with these things. There's the whole machine learning, AI aspects, data. There's so much out there. Hopefully, we'll get to discuss much more of this at the tinyML conference as well. Just to help some of our audience who may not be familiar with FPGAs, right? To me, could you maybe cover very briefly what is an FPGA and how is it different from a processor? And
Okay, yeah, maybe I'll start here as well. So an FPGA is a blank chip. It's a unprogrammed chip at its core. It's a logic resources that are interconnected together with some clocking capabilities, and modern FPGAs have some hardened functionalities like DSP blocks. These are multiply, accumulate blocks, embedded memory that typically is distributed throughout this programmable fabric. IOs and FPGA IOs tend to be on the flexible side. It can support many protocols. And nowadays you see more and more hardened functions added into the FPGA. Sreepada here is showing the Crosslink family, Crosslink NX family, part of the Nexus family at Lattice. And these devices have about 17 to 40K LUTs. LUTs is the logic cells or the programmable logic of the device. It's how an FPGA is characterized in terms of density. And then around you can see some of the other functionality, like a hardened MIPI D5 to bring in video data, IOs that can bring in other types of data, hardened PCIe to interface the rest of the system. And so these are the basics of FPGA. And FPGA is programmed through RTL, and there are other tools that help simplify design for FPGAs. But at its basic, that's what an FPGA is all about.
Any thoughts, Sreepada?
Yeah, that's a very good explanation. To put it in more simplistic way, in my view, it's like a canvas, right? So think of like we provide the canvas for you to paint. Okay, and all these are basically hooks where you want to hang up the paints, like IOs, right? So you can put it in various places depending upon what kind of interfaces you have and those kind of thing, right? So we have hardened many of these interfaces so that you get a very good performance, power, and very kind of for certain edge applications, right? So, for example, MIPI camera-based thing is very much required in all the application, and there is no point in implementing with LUTs and things like that, right? So we have hardened those kind of functionalities which are very much required to enable the tinyML, right? And then we provide, we will go over next few things. Like instead of providing a blank canvas, what we have done is we have put a certain painting already, so that yes, you get to feel the thing, but at the same time you don't have to start from the scratch, right? So there is already a platform for you to develop, right? So imagine like you are going and always you want to paint the scenic thing outside a landscape, right? So certain things are very common, trees and things like that. So those everyone no need to paint, right? So we have painted. You can add exactly what exactly you want to put there, right? So kind of thing. So that is how you can think of it, right? So it is more of a canvas with certain things already there and with enough space for you to do your own creative work and show your uniqueness in the product. Basically, that's how I would present it, right?
Okay, that's a very nice visual you painted there. It's quite easy to understand that way. So if I'm looking at it from the point of view of a developer, what is the reason that I would use an FPGA versus a microcontroller? What are some of the reasons why you should use an FPGA and when should you not use an FPGA?
Again, I would like Hussein to start with this. He has a nice let me see whether he has a slide somewhere.
I don't think I need a slide for that. So okay. I think the key word is efficiency. If you need to do a significant amount of compute, let's say video processing, AI applications, and this application is always on in nature, having an FPGA running this application is efficient in terms of power consumption. FPGAs are parallel processors that run at lower clock speeds, typical, for a low size or small size FPGA. You're talking about 100, 150 megahertz, and you can process a significant amount of video at that frequency. So at the end, the result is lower power. So when you compare a typical, class of a MCU with an FPGA of the same class, you're going to get more efficient performance out of the FPGA in the same application. Again, there are many applications. If we're talking about audio, for example, sometimes it might be simpler to deal with I'm really thinking in terms of AI processing. Might be simpler to think of an MCU as a good fit for that application. But if we're thinking about video, a significant amount of processing, and you're looking for flexibility in terms of what you do and how you clean up the video signal before you process it and how you post-process that, and FPGA has some significant advantages in this area. So I think that's how you can easily differentiate depending on your always on performance, like how much efficiency, how much power envelope you're trying to hit. It gives you an opportunity, and FPGA gives you an opportunity to create a system that is efficient to accomplish its goal.
So let me give one more dimension to that, right? So Venkat, to your question, why FPGA compared to other thing, right? So the thing is, one key aspect, everything what Hussein said is very much true. And on top of that, future proofing is what is very important in ML space. See, because there's so much research going on, every day you hear something new coming out and things like that. So if you are stuck with a technology that cannot mature so quickly, like you cannot adopt so much of innovation so quickly, then your product is also stuck, right? So, or even if you, let's say, ship and let's tomorrow you find a better way of doing the things and you cannot do that so easily, then you are stuck. With FPGA, our cycles are so small, like you can update the whole thing without adapting to new chip, right? So the whole FPGA is like you can erase this whole canvas and repaint the whole thing, right? So that's what basically it is, right? So FPGA. So it is more than a canvas. It's more like, think of even a whiteboard, right? So you can erase it, right? So with that kind of a thing, you have future proofing. When the new technology comes, when the new network comes, when things evolve, or even if you train with more data and things like that, you can easily go and deploy it. Right, so that's not true with all the technologies out there, right? Some of them, yes, they do provide, but there are things and limitations when things change so rapidly, right? So that's the one beauty of the FPGA.
Okay, so I think what you're saying is because the AI field is changing so often, there is new fundamental architectural changes every, I'd say, year, 2 years, right? That is too fast for the normal silicon cycle. And in order for a microcontroller with a hardened accelerator to be efficient, they will be efficient as a point solution, probably much more than an FPGA because it's hard ASIC type thing. But the moment the network changes, you may or may not be able to make use of the newer architectures, whereas in an FPGA, it is not, there's a little bit of overhead to this, but the gain you have is that you can go off and build hardware accelerators that are targeted for, say, RNNs versus CNNs, right? Where it's a lot different. Okay, that makes sense. So kind of we have one of the questions that is interesting, which I wanted to also talk about. Which is, and you mentioned this, which is ease of use, right? And there is the way I would think about it as a developer. Most likely, I know C or C++. How would I go about getting started with an FPGA? Because RTL, which is Verilog or VHDL, seems like quite a steep learning curve. So are there tool chains, are there ways that you enable customers to more easily adopt the solutions that use an FPGA?
Yeah, let me start with that. Maybe Hussein will have some point to add later. So basically, yes, Venkat, you are right. We recognize this very early in the stage when the new application or the new domain like machine learning comes out, right? It becomes a little hard to develop everything from scratch on FPGA. Of course, for the established technology, FPGA is in use from long time, right? It's not like something very recent also. FPGAs are there in the market and being used for many applications, right? So kind of thing, including space, right? So it's already there in the space also. It's very reliable from that standpoint. Now, having said that, yes, we recognize the difficulties. What we did is, instead of providing a FPGA as a commodity, we started creating solution stacks. Okay, basically what it means is, instead of asking you to, okay, go and here is the FPGA, let's and this thing, you can go and paint whatever you want. What we did is, we created an IP. Okay, so basically what we did is we created an IP that is very good for neural network inferencing. right? So and we understand our FPGAs better than anyone else, how to efficiently utilize all the available resources and what is the best way to do it. We kind of created this, right? So of course it did not fill up the entire canvas. Still you have a lot of space to do your own things, customization and things like that around this IP. But at the same time, you don't have to do it. Right? So basically, whatever we have canned solution we provide, that's good enough for most of the application, at least around vision. Right? So anything on the image processing and things like that, this IP and also even the peripherals like what we talked, DeFi and all those things are good enough to do the application. On top of this, what we did is we put in the design methodology, which is very easy to use, very simple to use, right? So basically what we said is, okay, so now here is the IP. Okay, now apart from that, okay, this is the traditional FPGA flow for those who are aware, right? So FPGAs are there now. People do create the RTL design, and then they take it through our Diamond or Radiant software, which has synthesis, place and route, and those kind of thing, and generate the final big files. And those who are not aware of FPGA, this is more like a firmware that runs on the FPGA, right? So they program it, right? This is a very traditional kind of thing. We kind of eliminated this almost entire this design cycle with this scanning of the IP, right? Once we have this IP design platform, you don't have to. We provide even the bit file for you to just put it on the FPGA. Okay, this one is an option. This became an optional step for the customer. Okay, if you want to use it, extend it, you are welcome to do that. But if you don't want to, if you want to use the CAN subscription, you can do it. On top of that, now this one is more like a processor kind of architecture. It requires instruction. Basically, neural network needs to be compiled and needs to be, because depending upon the application, you have different network topology, you have all those things that needs to be compiled, right? That for that purpose, we provided a flow which is basically a click button installation, because we had a very good experience in simplifying the design flow for all the FPGA use. Similar approach we adopted. Probably ours is one of the first tool chain which had a click button installation, right? So because anyone working on it, they suffer because there are so many open source packages, installing every package together and getting it working is a nightmare. We recognize that, and we provided a compiler which is very simple, GUI interface, and runs through it, right? So that makes the software flow very simple. On top of that, we provided additional framework that interfaces with the training, right? Because we can go in a little more detail later part when you have more questions on this, but we call it as Sensei Studio, which basically integrates the training part with basically the inferencing part, right? So considering some of the hardware capabilities and things like that. With this one now, this became completely software domain, or even the machine learning domain, right? So everyone who looks at this understand, okay, TensorFlow, Keras, I need to train the model. I need to just run through the compiler to generate. Even those who are familiar with the framework like TF-Lite and other things, they understand. Okay, so this flow is simple enough. So that way, we kind of made it very transparent that some of the complexities or whatever you talked about FPGA, or do I need to have an RTL expertise to use our Sensei solution? No, you don't have to. If you have some FPGA background and things like that, yes, it helps you to customize the solution uniquely and position it more uniquely compared to anyone else, right? So that's how we have to look at it.
I would add on the ML side, something that Sreepada didn't touch on is the model zoo that you see there. So over the past 5+ years, we've built many models, and these models have gone to production, and we take these models and we share them out. We provide them for users to play with them and create new application or improve on current applications. So the integration of Sensei Studio with a model zoo and a compiler is a software domain or ML domain knowledge that any ML designer should be able to follow. And as Sreepada is saying, on the FPGA side, we try to abstract that as much as possible by providing CAN solution. And we have other approaches as well. We have designer tools like Propel that helps you design a system grab and drop IPs and connecting them together. But yeah, providing just silicon alone did not make a lot of sense to us. We want to provide ease of use, and we kind of put this together, the Sensei stack, and we've been adding more and more pieces to it over the years. And these are hardware platforms that you can grab off the shelf and prototype with. IPs like the one Sreepada was showing, or accelerator engines, we call them IPs. We have many flavors of them. Software tools like the FPGA software tools and the compiler tools at Sensei Studio. Then on top of that is the minimum, it's the examples of reference designs and demos that you can use as a starting point. And all of these are around different class of FPGAs. You know, in the bottom, you see all the way in the left-hand side is the IS40 Ultra Plus, simple object detection type of device. And in the bottom right-hand side is ECP5 type of family where you're doing more processing. And we have additional families. I don't think they would belong exactly into the tinyML domain, but we have multiple families that are part of the Sensei stack. So software, tools, solution stacks, examples, IP cores, hardware platforms are all the pieces that we put together to enable ease of development with FPGAs.
So as a designer, or a developer, if I wanted to incorporate some of this, usually the first thing I do is buy a developer kit, and then try out what's available and then start making changes. So I think what you're saying is that this sort of system is there all the way up from the FPGA itself, which is the silicon, but also all of the other things that really go to make up a complete solution, that you provide something of this sort. And that so is source code available as well? Is it open, or how much of it can I really go and make changes to?
Yeah, so basically the source code, in the sense, like it depends where you are talking. See, for example, reference designs, right? We provide the training script, even the models, right? So you can even modify the models, and these Python codes and all those training things are available, right? So most of the time, right? Of course, there are cases when we cannot fully expose and kind of thing, but many of the things we understand it is required for our customer to understand in detail what is feasible, what is not feasible, and those kind of things. It is available. Now, in terms of the software tool itself, yes, most of our tools are easy to use, but at the same time, they are not open source as such, like design tools, what we are talking here, right? So it's not like where you can, and it does not make much sense to modify, for example, the compiler, right? So because it is so much tied with our platform FPGAs and the neural network inferencing engine we have created, it does not make much sense to go and modify those things, and it becomes a kind of thing. So that's why we don't open source that, but definitely something. So, and then in terms of the RTL, the core IP itself is not open source, the neural network inferencing engine. We provide enough details, but there are peripherals that we make it open source as part of reference design, right? So, for example, this stitches with many of the image processing application, pre-processing as well as post-processing and things like that. Those things, RTLs are available in many cases as part of the reference design that we talk here, right? So, kind of thing.
Okay. There's a couple of questions that have come up. One of them is power related. So I think you have a little bit on here. Do you want to talk briefly about that? Just the power scales and typical power for an actual application, right? So this would be this excluding the sensor power. So if let's take like a typical object detection, human presence detection, right? What is the range of power I can expect? And for just the FPGA part, that includes its power supply, the whole FPGA. Exclude the sensor, for example, things that are common.
Sure, let me answer that. So in production today, human presence sensors type of devices that we're in, we have multiple power capabilities. So we can run the networks and the design at slower speed for if there was no person for a certain amount of time and we're waiting for arrival of a person. We can get down to about 10 milliwatt or so, running 2-3 frames per second, checking for availability of a person. Once we have a person around, we can go to another performance level where we're continuously tracking the movement and availability of the person. And this is a complex network that is fully aware of the user and their head movements and things like that. And that's the 100 milliwatt power envelope running at 30 frames per second types of speed. So
and what kind of resolution do you think that would be at?
The input resolution, there are multiple networks that run in this case, and the input resolution would be starting with 224 by 224 for the first network. And as we, the second network is getting a region of interest or something like that for further processing, and that could get down to 128 by 128 or 96 by 96. And we decide which network to run and how much time to spend between those networks. That part is fairly flexible. It's part of deciding how to create a good user experience for the end application itself. But yeah, that should give a good estimate. 100 milliwatt on a crosslink NX type of device running some really significant processing 224 by 224 at 100 milliwatt range of power.
Yeah, so basically in each of the reference design, right, we provide a lot of details about like what resolution this network and how much power consumption it is doing, what is the frame rate. So because the thing is we target, see, there are multiple variables here, right? So one is the network, another resolution, and then the FPGA itself. We have families of FPGA. We are not talking about one device. Okay, so we are even in a tiny space that we are talking, right? So outside of the tiny space, we have more devices. Even in the tiny space, we have multiple options, right? So multiple devices available and things like that. Depending upon the target and things like that, it varies, right? So the same network kind of varies. So that's why it will be slightly misleading if we give one number kind of thing. Definitely, there will be more information as part of these reference designs in the model zoo. Worth taking a look at it, whether it meets some of the requirements that you are targeting and things like that. Right? So,
yeah, I think I was trying to give an example, a concrete example, because it really helps. I think Sreepada is correct. If you look at again at the IS-40 Ultra Plus at the extreme. For Lattice in terms of performance, you can get much lower than that and still get 128 by 128 type of performance out of that device.
Wow, that's pretty impressive. And the ability to change things. Okay. This question that Mike has, what are your ResNet 50 test results? Perhaps I'm not sure how to generalize that question.
okay. So let me take I have not looked at the question, but let me take it based on what you read. Okay. So basically, what we do is not necessarily all the network that is published as part of the paper is good for the kind of thing. That's why the model zoo plays an important role, right? So we kind of optimize it and that kind of publish what models are good and how to further. See, this optimization is not just in one place, not in just silicon, just not in this IP that we are talking here. The optimization is not just there. Not just in the tool. So it's across the whole stack, right? So we do the optimization across the entire stack, right? So in every place, the kind of thing, right? So again, as we mentioned, even for ResNet 50, let's say, okay, if I give one number today, that will be very misleading, because here, just to give example, right? We have multiple families. In some families, for example, we trade off between how much basically memory you will put in each of the chip. Okay, in one chip there may be more internal memory, and you will be able to perform, okay, a faster thing at a lower power thing. But is this a good for all application? May not be the case. There may be application wherein you don't need this kind of thing. You need more of a external DDR interfaces where you can learn even larger network and things like that. Power is not so much of a concern. Even ResNet 50, you can run in both the cases, right? So internal and versus kind of thing outside and kind of thing, right? So depending upon basically what technology you choose, right? So it changes. The answer changes. That's why, I mean, it's very hard to give one specific number in the meeting. It's definitely, but those informations are available kind of things, right? In some cases, it has to be extrapolated. I'm not saying that we have data for all the network available there. We have published it. That's not the case, okay? I mean, that's not even feasible for us also. But some of the things can be inferred, okay? So if we have ResNet, even a smaller ResNet, for example, let's say, okay, it's a replication. So basically what happens is same pattern gets replicated to create a deeper network to get a better accuracy and things like that. So easily it can be inferred. Okay, for this many layers, I'm getting this performance. What will be the performance for if I add more layers, right? So that kind of inference can be done. Right? Even tools provide it. If you provide a thing, you don't have to run it on the silicon and we do the profiling, right? So you feed it to the tool and get the target, like you target it for a certain silicon and things like that, you will get the profile basically for that network.
So if I could paraphrase your answer, I think you're saying that in order to get say ResNet 50 as the example, to get the power number will really depend on which family and how you implement it, because the silicon itself is flexible, and therefore the exact power number will depend on multiple trade-offs in the stack, which is where are your weights living? Is it off chip or on chip?
Yes.
And what kind of performance are you targeting? Are you targeting very high performance, or you really don't need that performance? Therefore, the hardware can actually change.
Yes.
I think it's good to focus on the applications. What is it that you're trying to accomplish? What is the power envelope you're trying to hit? And we try to compile a number of network and provide a number of devices that can solve these problems. So, you know, looking at ResNet 50 or MobileNet or something like that, just what is the power for that? It's a very general question, I think. We need to get deeper into what application, what power envelope you have, what, you know, and then like Sreepada said, we have multiple families within the FPGA devices that can handle different applications.
Yeah, so just to give one more example, for example, right? I'm just jumping a little ahead with the use case illustration here. See, for example, we have this predictive maintenance. Okay, so which is basically, okay, estimate the life expectancy of the motor when motor requires maintenance, right? So this one is more like a background process, right? So you don't expect, okay, immediately, we are not detecting the failure here. We are expecting when the maintenance is required, right? So the predictive maintenance which can run in the background while you are processing a lot of other things, right? So in that case, what we did is we interfaced our engine, the same thing with a RISC-V core with a cut down version, right? So we provide this scanned version again for our user, and then basically this gives a different performance compared to the whole thing, right? So now, based on your end application goal, the right way is, that's why I said the tool methodology plays a key role. You should be able to quickly run your target network when even it is not fully ready, multiple iteration, and get some numbers, okay, and do the profiling and say, okay, is it meeting my requirement? Is the way to look at it, not just looking at the data sheet that normally gets published. Okay, so yes, as part of the whole game, we have to publish some data sheet. We also do like any other company. But as an engineer, right, my recommendation is not just look into only those data sheet, right? That's sometimes they are misleading. So once you have an easy to use design methodology, if you have a basic network or kind of thing ready, run it through it. It gives you some numbers and things like that. Use that in your whole planning, right? So evaluation kind of thing, not just looking at the numbers.
Again, thinking about applications, yeah, if you can go back to the slide 4 here. No, stay on the slide. So you see these Certus Pro devices are actually there in the system to run the motor. Their main function is a motor control function. And they're fairly efficient in doing that function, given that there are DSPs and other blocks that help, and FPGAs are used for motor control. In addition to that, you can have these devices running this background task of understanding the quality of the motor. Is the motor going to require, predict if the motor is going to require service at some time. So it's important to have an application, holistic application view of what's in the system, what it's trying to accomplish, and then how can tinyML or ML in general help solve other issues, whether it's a background task or part of the actual processing pipeline.
Okay, that's I think so. The way I think about this is, as a developer, if I deployed something in the field, I can add on to the functionality or change the functionality which goes towards the flexibility. If I had a microcontroller doing this, then also that flexibility is there, but it's in a different dimension. There I'm writing C code, and at some point I'm going to run out of, hopefully I haven't filled up, I haven't hit the full capability of the processor. So there is some overhead I have to account for. An FPGA also allows the same sort of thing, but in a fundamentally different way. Also, it does, of course, extra C code, but also you can change the hardware architecture itself to make up for any new features that might need to be added.
Yeah.
I think I had requested Hussein and Sreepada to also have a couple of concrete examples. I think we're a little bit short on time. Maybe we can, there's one more question that I'd like to bring up from the audience, which is, do you have simulation data to back up the comparison between FPGAs and embedded processors?
Okay, so let me start with that again, right? So this benchmarking is slightly misleading. Okay, so most of the thing, again, like many people talk about tops and all these things and kind of thing. So there is always, you can publish the numbers like a skewed kind of thing. It's very tricky to do that comparison across different technology. Now, what is the testimony that the thing is this? Now, some of the things where it is getting used. See, for example, our technology is currently in production, right? And in what kind of application it is in production, okay? Then basically, that is a testimony that people have already done good amount of benchmark considering the end product, what needs to be delivered, and saying, okay, this is the right technology to use it. Okay? So to give an example, FPGAs were there in usage for many industries. But if you come to client compute, okay, in the client compute, it was not so popularly used, like in laptop and things like that, right? Now, today, our FPGAs are used in a laptop and other things that are getting shipped, basically for ML reasons. because they want to enable the ML using our tiny FPGAs on these client compute devices, right? So kind of thing. Now that gives you some kind of idea, okay, so where our technology stands with respect to other technology. If I just go and publish some numbers today, definitely I can pick up some numbers, but that's not a good reason why you should be adopting this technology. Right? So that is a more solid reason, proof of concept or in the productization that should back you to mitigate some of the risk. Right. So that's basically my take on it. Hussein may have a different answer for that.
Yeah, I think what's important is the flexibility of an FPGA, ability to change your engine and keep up with an ever-changing world of AI models. Venkat earlier said things change every couple of years. I think things change every couple of months, actually. So not only the AI models are changing, but the applications are changing, and we find end users are interested or looking to get delighted with the experiences. OEMs are also looking to do that type of sort of stuff. Also, the variety of applications. So Sreepada here has an application where is doing a case study on barcode detection. So there is a variety of applications that you can accomplish with one FPGA with the same device. So that type of flexibility you only get from a programmable device versus an MCU type of a solution.
So why I put it this use case is basically one of the things that we have done is we have seen success in some of the ML areas, and we are doing the proliferation of this, okay, in across a different market segment. Like, see, for example, we have been very successful in detecting the humans and all this thing, right? So, and many have also demonstrated that. Now we are proliferating that. Okay, now you can, instead of detecting human, we can detect the barcode, right? So you can take the same network, and instead of just publishing kind of thing, we kind of demonstrated that, okay, now you can adopt the same network and basically same tool chain and everything. We provide all the required solutions to train and do the transfer learning and other things. On top of that, okay, when you notice, okay, this is not good enough for whatever reason. Okay, let's say barcode, the boxes are moving at certain speed and at a certain distance, you need to change the network itself. Still, you can do that, right? So you can start with something known, okay, something which is well proven. Basically, that's what I'm trying to say. You have a canned and proven solutions. You can take that, experiment it, and see whether it meets your application requirement. When you find it does not meet, you have a easy way to do the changes that are required, right? So it could be even latest network topology that you want to adopt. In our case itself, we went and when we published earlier, YOLO v5 was not there, right? So YOLO v5 came more recently and things like that. And then we kind of adopted some of the network topologies and supported it, right? So the new application with certain application requirement and things like that. So that way, basically what it is start with something known, okay, and then make the changes, and then you have an easy way to get all the required measurement profiling, right? So that's the right way to do the thing.
Okay. I think we're out of time. There was quite a bit of stuff we could have talked about. So I'd like to conclude our first discussion. Thank you so much, Hussein and Sreepada. I think, and thank you to the audience as well for the interesting questions and the engagement.
Thank you, Venkat.
Thanks for hosting.
I wish you all luck with this series. It's very interesting and glad to be here.
Thank you. Thank you very much for your attention. And let me proceed with the outro slides. I will just acknowledge the sponsors. So I would like to thank all of our tinyML strategic partners for helping us leading tinyML to the next level. And I will name them one by one. We would like to thank the executive strategic partners, and specifically AgentPulse, the leading development platform for AgentML. I would like to thank Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, making edge AI a reality. We would like to acknowledge our platinum strategic partners, Renesas, Sony, deploy Vision AI at the edge at scale. Thanks to our gold strategic partners, Analog Devices, what if becomes what is. Arduino Pro, easily deploy your tinyML solutions with Arduino Pro. ARM AI, powering tinyML innovation. Inatera, this is one of our new sponsors. Neuromorphic Intelligence for the Sensor Edge. Microsoft. SensiML. ST Microelectronics. Synaptics, engineering exceptional experiences. And we would like to highlight our silver strategic partners, AZIP, Compass Marketing, Greenwaves Technologies, Groverty AI, IBM, Imagimov, Nota AI, NXP, OctoML, Poland Technology, Kitso, Schneider Electric, Silicon Labs, and TDK, that is part of Kitso. Thank you very much all for joining us today. Today was the kickoff of our new project, new series, tinyML Builds. I would like to thank Sreepada and Hussein for a very interesting interview and for sharing their experience with us today. And thank you very much, Venkat, for being our host and for your wonderful moderation of the series. So the series will be on a monthly basis. So stay connected and do not miss our next edition next month. Thank you very much for your attention. Have a wonderful day ahead. Goodbye.
Thank you.